The authors of the Journal of Physical Chemistry Letters paper, Asif Equbal, Miranda Lee, Tarnuma, Tabassum, and Songi, will take turn to share with you highlights of our study. As suggested in the title, we report on a crossover of the dominant DNP mechanism from the expected solid effect to the unexpected double mixing regime as we increase the concentration of the Trityl-OX063 radical used as a polarizing agent. Most critically, we experimentally ascertain diagnostic signature of double mixing DNP using high-field pulsed DPI line shape and pump probe Eldor experiments. So the debate and the hypothesis about thermal mixing has been there, but having diagnostic experimental signatures is what really adds to the value and understanding of this study.
Generally speaking, there are 4 DNP mechanisms: Overhauser effect, solid effect, cross effect, and thermal mixing. The Overhauser effect, or OE, and the solid effect, or SE, mechanisms are based on the transfer of spin polarization via processes involving one electron spin and one nuclear spin. OE requires dynamically driven electron-nucleus cross relaxation, and therefore is normally not anticipated as an effective mechanism in insulating solid. SE, in contrast, can theoretically be achieved under a broad range of experimental conditions, but is practically inefficient at high magnetic fields because it requires very high microwave power, a limiting factor with the current available instrumentation. DNP mechanisms relying on the allowed flip-flop transitions of more than one electron spins are more feasible, as their effect can be enhanced with strong EE coupling and better exploit with lower microwave power. One such process is the simultaneous triple flip of 2 coupled electron spins and a nuclear spin, achieved when the frequency difference of the 2 electron spins matches the normal frequency of nuclears coupled unequally to both the electron spins. A keystone feature of the triple flip mechanism is that it does not require microwave to drive the flip-flop-flip transition. Rather, microwave irradiation only serves to create a large net polarization difference, or delta PE, between the electron spin pairs separated by the nuclear normal frequency across the electron paramagnetic resonance, or EPR, line. The amplitude of nuclear spin polarization is then proportional to delta PE. Cross effect, or CE, and thermomixing, or TM, are 2 DNP mechanisms that both rely on this triple flip process. The major difference between the 2 mechanisms lies in the requirement of the EE coupling, where thermomixing requires large EE coupling on the scale of nuclear normal frequency. Knowing in the electron spin dynamics is critical to understand the DNP mechanism. In the Han lab, we are equipped with in situ EPR detection integrated with a 6.9 Tesla DNP NMR spectrometer. There are some standard or essential EPR experiments we conduct to obtain the insight of the electron spin system. First, we measure the electron spin distribution as a function of the magnetic field or microwave frequency. Second, we find the microwave saturation probability of the electron spin packs. This can be hinted from the electron longitudinal relaxation rate measurement using an experiment such as inversion recovery. Third, we need to know the nature of the electron spin coupling network and ultimately electron spectral diffusion, or ESD. This is because the efficiency and viability of thermomixing DNP relies heavily on the topology of the electron spin coupling network. The EE coupling network and electron spin diffusion, or ESD, can be reviewed by an electron-electron double resonance, or Eldor experiment. With all the necessary background information, we now explain our experimental results.
In our study, we have systematically investigated the optimum DNP mechanism in Trityl, which is a water-soluble radical and widely used under dissolution DNP conditions. At a high magnetic field, only the solid effect DNP mechanism is expected to be operative for the protons. For instance, at a magnetic field of 7 Tesla, the solid effect mechanism results in DNP enhancements at an offset of plus or minus 300 MHz from the Trityl center frequency. This is reflected in the enhancements at 193.3 and 193.9 GHz, obtained using a concentration of 10 millimolar trityl. However, contrary to expectation, there is a small enhancement which is dispersive in shape even at the center frequency. This cannot be attributed to Overhauser effect or cross-effect mechanisms as per their well-established definitions and requirements. That leaves us to assume that the mechanism at play is thermal mixing, under the hypothesis that radical self-assembly or aggregation leads to a strong electron-electron coupling network, and in turn, thermal mixing DNP. This is also reflected in the increasing thermal mixing probability, that is, the enhancement at the center frequency with increasing radical concentrations. However, we cannot prove this hypothesis using merely the NMR measurements that are shown here. Since the source of polarization is electrons, EPR measurements would provide us more insight into the underlying DNP mechanism.
In literature, there are a couple of theoretical predictions made on the existence of thermal mixing DNP in narrow-line radicals. Early in 2016, Walter Kuchenberger from Nottingham did a thorough quantum mechanical analysis to understand this phenomena at microscopic level. His theory predicted that TM-DNP required a large asymmetry in the dipolar broadened EPR line shape, and the required asymmetry in the line shape comes from an asymmetric EE coupling network or some other heterogeneous interactions such as G anisotropy. Asymmetry helps in maintaining a large polarization gradient under microwave irradiation and thus induces a large DNP enhancement. Using our 7 Tesla dual EPR NMR spectrometer, we were able to measure EPR line shape of trityl radical under the DNP conditions. Clearly, with increasing concentrations, the asymmetry in the line shape increases, as seen here, and this validates the theory as well as provides a clear experimental signature for TM-DNP. The other EPR signature comes from the Eldor measurement that was introduced to the DNP community by Daniela Goldfarb and Shimon Vega at Weizmann Institute. They recently predicted that in this regime of strong E coupling network, there will be a microwave-induced hyperpolarization of electron-spin in the Eldor experiment, resulting in the lowering of spin temperature of select electron spins as reflected in the left panel. Clearly, the experimentally recorded EPR Eldor experiment with our setup confirms the theoretical prediction on thermal mixing DNP. A large hyperpolarization of electron spin is observed at 40 millimolar trityl radical, where the dominant mechanism for DNP is thermal mixing.
So thermal mixing DNP has exciting spin physics that is operational, but at the same time it has huge practical utility as a tool because significant proton DNP enhancement is achieved at low to moderate microwave power. This is shown here on the left and right with a DNP profile as well as a DNP power curve, so enhancement versus microwave frequency as well as enhancement versus microwave power. And you can see that a solid effect is far from saturating at our available microwave power, but at around 200 milliwatt at the source, thermal mixing effect already saturate. It is achieving effective enhancement. And this is because thermal mixing relies on a loud transition and utilizes the coupling of many electron spin that whose strong coupling of several electron spin facilitates the DNP transfer efficiency from electron to proton spins. We come to the conclusion, we found surprising crossover from solid effective thermal mixing using the widely used Trityl-OX0 radical by tuning the concentration. And the concentration basically is helping us go from an isolated electron spin to strongly coupled electron spin. We were able to clearly assign thermal mixing DNP as the operational mechanism based on pump probe ELDO experiment, as well as high field EP aligned chip analysis, in our case, pulsed echo detected EP aligned chip analysis that showed us together, sort of ELDO and the high field EPR, that we have an asymmetric population, some of which actually get hyperpolarized during pumping. And finally, thermal mixing DNP is exciting as a real application, has application potential because of its low microwave power requirement and high signal enhancement. Finally, we would like to thank other students and postdocs who contributed to this work, besides the authors, of course, namely Dr. Shital Jain, as well as Khan Tagami and Raymond Siglin, who are always continuously improving the instrumentation and always contributing to good debate in our lab, as well as early on continued discussion with Dr. Akiva Feintuch and Dr. Shimon Vega for helpful advice and lively discussion on DNP mechanism. The funding comes from the National Science Foundation, from the Chemistry Division, as well as the Binational Science Foundation between Israel and the United States funding basic research. So thank you for your attention.